last time we met, we had been talking about intervals that were increasing and decreasing and constant, and then we talked about the different types of extrema. So we talked about maxima and minima, and then local and global, right? What I want to start with today is talking about how we can use our graphing calculator to do this. So we're continuing on from where we were in section 4. So let's say that we have the function f of x equals x to the fourth plus 2x cubed minus 4x squared minus 3x plus 1. And let's say that we want to find, all the information about this relative to like the increasing and decreasing and extrema. So we want to find the max and mins, determine whether they're local or global, and then write also the intervals of increasing and decreasing and constant. Sound good? And all you're given here is this equation. What should we do first? Okay. Plug it into to do what with it? To graph it, yeah. So let's look at the graph. So to type this in, I press the y equals button to get to graph anything. And then I'll type the x button, which is right here next to the alpha. And then to make the exponents, I'm going to use this caret up button. So you see it's moved my cursor into the exponent. So I can type in the 4. Now you see the cursor has this right arrow on it. To get down out of the exponent, we'll press that right arrow, and then I can continue typing. 2x, and then caret 3. Press that right arrow to get back out of the exponent. Minus 4x, and now I could do caret 2 to get the x squared, or there's a shortcut here for the squared right on the home row, and that's like 3 less buttons I gotta press, so I'm going to go with that route because it's less work for me. And then I finish that up by just typing minus 3x plus 1. Probably the best way to graph is to do the zoom standard. So I'm going to press zoom standard rather than picking a window. So if I look at my graph here, how many maxima do we see? 1, right? Where is it? It's this spot right here. Everybody agree? Is that local or global? Local. Good. Okay. And that local max, let's find the coordinate for it now. So the calculator can do this for us. So what we'll do is we'll press the second button and then the trace button. That's going to open up the calculate menu. And the command I'm looking for, if I'm looking for a maximum, is maximum. Not a surprise there. So I'll pick command 4. So you can either scroll down and press enter, or you can just type the number 4. Either would have worked there. Now if you look at the bottoms of our screen on our calculator, the calculator is going to ask us some questions. So the first question is left bound. What the calculator is trying to get at is where should I be looking for this maximum? What range of values? So the left bound is I just need to pick some spot on my graph left of where that maximum is. So you see my cursor has popped up here right where my arrow is. There's a little flashing cursor. It's kind of hard to see. What I'm going to do is I'm just going to use the left arrows to move that so that I know that it's on the left side of that maximum. So like anywhere over here is good. Doesn't really matter where it's at. You just have to make sure that it's on the left side of it. Okay. Once you've moved it to a spot you like, you press enter. Next it asks for right bound. So it's the same idea. I'm just going to move that cursor over to the right side of that maximum. That looks good to me. Definitely right of it. So I'll press enter. Then it says give me a guess. So I could move my cursor really close, but the guess doesn't really matter. Any guess in between the left and right bound is fine. So I'm just going to press enter because it's, again, less moving around. And it tells me my maximum is the point, negative 0.32, comma 1.50. And I just rounded these to 2 decimal places. The directions you'd have would tell you how to do that rounding. And if they didn't tell you to round, what should you do? Write the whole thing. It's no big deal, just some numbers, right? All right. How about the minima? How many minima do we see? 2. Okay. And what is any of them global? Yes. So I have 1 global and 1 local, right? Okay. Which one is the global, on the left or the right? The leftmost one. Good. Let's find that one first. So we'll go back into that calculate menu. So I'll press second and trace. Which command do you suppose I'm looking to use if I'm going to find a minimum? Minimum command. So I can scroll down to that and press enter, or just type the number 3. So again, it's going to ask me the same 3 questions, left bound, right bound, and guess. So I'm just going to start by moving my cursor to the left of that minimum that I'm searching for. So we said we're going to find the global one first. So really anywhere over here would be okay. So that looks good to me. Then it wants a right bound, so really anywhere over here would be okay. So just move that over. That looks good. Press enter. And then a guess. You can just guess at the same spot and press enter. So supplying a better guess really doesn't make anything, or doesn't make any difference. I mean, like, the calculator reports its answer slightly faster with a better guess, but it's so little time you'd never even notice it. So, like, it takes definitely more time to move the cursor to make a better guess than it would to just make a bad guess and let the calculator run for like 3 microseconds longer than if you had a good guess. So, like, don't waste your time. Everybody okay with that? Okay, let's find that other minimum. So again, we'll go second trace, minimum command, and then we need a left bound, a right bound, and a guess. Whoa. Okay. Come on here. Calculator's got a mind of its own here. Okay, finding a left bound. That looks pretty good to me. I'll press enter. Now right bound. That looks good to me. Press enter. Guess. Press enter. And there's my minimum. Everybody okay there? Okay. So looking at this picture, do we see any intervals increasing? Definitely do, right? Okay. So my first interval increasing looks like it's right here, from the global minimum to that local maximum. Everybody agree with that? So that interval goes from negative 2.24, right, the global minimum, to the local maximum. So that would be negative 0.32. And I'll write my union because there's more than one increasing part. I also have an increasing part right here. Everybody agree with that? That starts from the local minimum and goes to positive infinity. And remember, for these increasing and decreasing constant segments, we're always using parentheses. You won't ever use a bracket here. Everybody happy with that? Questions, ladies? You're good? Okay. Next we'll do decreasing. We see decreasing parts, right? How many decreasing parts do you see? 2. I agree. We'll start on the left. The first decreasing part is this part that goes from negative infinity to that global minimum. So that's negative infinity to negative 2.24. And then my second decreasing part happens from my local max to my local min, that part right there. Everybody agree with that? So we'll go 1.06 to I'm sorry, that's the second part. Negative 0.32, thank you, 1.06. And do we see any constant parts here? Nada, I agree, no constant parts. So for us, if we wanted to, on a test or whatever, I would either give you the picture already, like you saw in the homework, or I would give you the function and expect you to be able to use your calculator to fill in the values and to do this kind of thing. Okay? So either one of those I think is fair game. The calculator should be pretty doable though, right? That wasn't too bad. The hardest part is probably making sure you get a decent window, but Zoom standard, if your teacher's not a jerk, should get you a window that you can view the function in. Okay? So that'll close up section 4. We'll start talking now about section 5. So section 5 is about symmetry. And we really have 3 types of symmetry that we'll talk about here. The first kind is symmetry with respect to the x-axis. So I'm just abbreviating that common mathematics phrase with respect to with the letters WRT. And just as kind of been our pattern, we're not going to give like the really formal, rigorous definition of what we mean by this. Instead, we're just going to kind of draw ourselves a picture, because primarily what I'm going to want from you guys is that you're able to like know it when you see it, kind of thing. So this is an example of a graph that's symmetric about or with respect to the x-axis. When we say that, what we mean is if I take 1/2 of the graph, like the part above the x-axis, and I reflect it across the x-axis, it should lie exactly on top of the other half. Everybody okay with that idea? Okay. Should be easy to kind of see that visually, right? The second type is symmetry with respect to, guess what? Y-axis. Oh my gosh, it's so shocking. So the same idea. Here, if you look at one half of the graph and you fold it over across the y-axis, it should lie exactly on top of the other half of the graph. Everybody okay with that idea? Okay, good. If we compare the graphs here that are symmetric about the x-axis and symmetric about the y-axis, do you notice anything about one versus the other? Think about the things we've already talked about. What can you say about the graph, the first graph? Yeah, that it fails a vertical line test, which means it's not a function. Is there any way that you can have a function that's symmetric about the x-axis? No, right? They're all going to fail a vertical line test if they're symmetric about the x-axis. None of those things will be functions. Everybody okay with that idea? How about if they're symmetric about or about the y-axis? Will they all be functions? Not necessarily. So consider, just for an example, what if our graph looked like this? That's certainly symmetric about the y-axis, right? But it also fails a vertical line test. So the symmetric about the y doesn't guarantee that you're a function, but it could be. It could be. Symmetric about the x guarantees that you will not be a function, though. Everybody okay with that idea? Okay. The last type, which you might be going, you did x and you did y, what are you going to do now? Well, this one has kind of a long name. It's 180 degree point symmetry with respect to the origin. And I get that that's kind of a mouthful of a name. The idea, though, is not so hard. So this is an example of something that has 180 degree point symmetry with respect to the origin. So since it's with respect to the origin, I'm going to imagine that I'm anchoring my one half of my graph here at the origin. So I'm going to just be thinking about this part that I've highlighted in green. If I rotate that 180 degrees while it's anchored to the origin, it's going to lie right on top of the other half, right? You can kind of see that. Again, very visual, but should be fairly realistic. Everybody okay with that idea? These situations where we have symmetry about the y-axis and this 180 degree point symmetry with respect to the origin also have special names. So we call the symmetry with respect to the y-axis even functions. and symmetry with respect to the x-axis, I'm sorry, with respect to the 180 degree point symmetry with respect to the origin is an odd function. So note that this doesn't, at first glance, have anything to do with our concepts of odd and even we have from arithmetic. Everybody agree with that? There doesn't seem to be anything odd or even about this, like 1, 3, 5 are odd and 2, 4, 6 even. Doesn't seem like that's related in any way, right? The y-axis symmetry? Yeah, you're welcome. Well, let's look a little bit closer because there is kind of a relationship here involving odd and even still. So we've seen graphically what we mean by symmetric about the y-axis. Algebraically, what we mean is that the y-coordinates from our negative x's should be the same as the y-coordinate from the positive x, right? That f of negative 2 should be the same as f of positive 2. Everybody agree with that? So again, like if this is the point 2, 4, this should be the point negative 2, 4. Everybody kind of see that? The way we write that is that we say f of negative x should equal f of x. Because remember, when we write them, f of x is just another name for y. So these are just like x comma f of x's. Right? Are those 2 points there? Everybody okay with that idea? Similarly, we have a similar statement that we can make for these odd functions. So if this is, say, the point 2, 8, over here would be negative 2, negative 8 is the kind of the equivalent. So what we can say here is f of negative x equals negative f of x. So again, this is like my x comma f of x over here. This is my negative x comma f of negative x over here. So 8, or negative 8, should equal 8 when we make it negative, right? Does everybody kind of see that? Is still describing the same picture? Okay. So, if I'm given the function, say x to the 4th plus 1, and I want to determine whether this is odd or even, I can do a couple of things. The first most obvious thing I could do is to graph it on my calculator and look at the picture, right? Because we have a good visual understanding of what we mean by odd and even. So if I fire up my graphing calculator here, and I type in x to the 4th plus 4, and then again we'll just graph that on the standard window, we get this. Does this look even? That's what I think it looks like to me too. Symmetric about the y, right? What if we didn't have access to our calculator? What would we want to do to show it was even then? if we don't have our calculator or don't have access to a calculator, we're going to use this relationship. That's going to be our goal. Okay? So what I want to do is I want to figure out what f of negative x is. And if it's the same thing as x to the fourth plus 1, I know that this is an even function. Everybody okay with that plan? Okay. As an aside, if I asked you to do f of 2, what would you do? What does that mean when I write down f of 2? Hannah? Great. So I would plug in 2 for x, and I would say that's 2 to the fourth plus 1, right? If I did f of negative 2, what would I do? Yeah, the thing you have to be careful about there is that the negative sign needs to be inside the x to the fourth. That we have to make sure we apply the negative before we apply the exponent. So if I do f of negative x, all I'm going to do is plug negative x in for x, and I get this. Just like we did for 2 and negative 2, I'm just doing it for negative x. Is that okay? Now I can simplify negative x to the fourth. What that is just negative x times negative x times negative x times negative x, right? What do I get when I multiply 4 negatives together? A positive, right? So I multiply the first 2 negatives together, I get a positive. I take that positive and multiply the negative, it's negative. I take the last negative and multiply that negative, I get positive, right? So I'm going to get just x to the fourth plus 1. Everybody agree with that? Okay. And notice that this is exactly what we have here. So that is what we've shown is that f of negative x equals f of x, which was what we need, was our definition for even, right? Like that's the algebraic interpretation rather than the graphical interpretation. Remember, we wrote that down up here. Yes, Hannah? You don't plug any numbers into it. This aside was just to remind us kind of what we do when we have like f of something, how we do that. So it had, the 2 and negative 2 had nothing to do with this problem per se. It was just me reminding you like what you do with that notation. Good question. So let's do one more. I shouldn't say one more. We're going to do 2 more. So let's say we have 2x to the third plus 3x. I'm going to start the same way. Let's look at the calculator first and look at that picture to get an idea whether we think this is odd or even. Why don't I have to worry about symmetric about the x-axis in this case? Why am I only concerned about odd or even? Why can I ignore that first type of symmetry? Well, if I look at 2x to the third plus 3x, what name would you give that sort of equation? We talked about these last year in Algebra 3-4. Starts with a P. We spent a long time talking about them. Polynomial, right? And what do we know about polynomials? They are a type of function. What did we say if it was symmetric about the x-axis? That it can't be a function, right? So since I know this is a function, I can already ignore the symmetric about the x-axis possibility, and I'm limited to whether this is odd or even or neither. Okay? So we'll graph this. Again, I'll do zoom and then standard and look at my graph. What does this look like? It looks like that 180-degree symmetry or an odd function. We can use those two terms interchangeably. And again, we got this by just looking at the calculator. And I will play the same hypothetical game that we played before. Suppose we don't have the graphing calculator. Could we do this without it? Absolutely. To do it, we need to use this relationship. So just like I did for the even functions, I'm going to start by computing what g of negative x is. So to do that, what do we have to do? Good. So we're going to plug negative x in place of the x's. Notice here that I'm being careful in putting a parenthesis around each of these negative x's. Everybody so far so good? So notice that negative x to the third. What does that simplify down to? How many negatives are we multiplying together? 3, right? What do I get when I multiply 3 negatives together? A negative. So that first piece is just going to be negative 2x cubed. Everybody agree there? And then what do I get when I do 3 times negative x? Negative 3x. Everybody agree? Now let's just point out again what we're trying to get. We're trying to get negative f of x. So what I'm going to do at this step is I'm going to factor a negative sign out. So when I factor that negative sign out, the 2x cubed becomes positive, and the 3x becomes positive. And if I check this versus this, what do we notice? They are identical. So this is indeed negative f of x. Oops. We called this g of x. Negative g of x. But those two things are equal, and we've shown what we needed to show. Okay with this so far? Okay. I want to point something out. So if I look at these two polynomials, what is the degree of the term x to the fourth? Do you remember what we meant by degree? We talked about this a lot last year. Okay, the degree is the exponent on the variable. So in this case, it's degree 4, right? But if I look at this piece, what's the degree on 1? 0, because there is no variable. What can you say about the degrees of both 4 and 0? What kind of numbers are those? Starts with an E. Even. What type of function was this? Even function. If all the degrees of the terms are even, you should have an even function. So let's look at the last example we did. Let's look at the first term. What's the degree of this first term? 3. What's the degree of this second term? 1, right? Because we have an x to the first. Both 3 and 1 are odds. if all the degrees are odds, you should have an odd function. So we didn't initially, these terms odd and even didn't seem like it had anything to do with the normal odd and even that we thought of when we think of odds and evens. But it kind of does, right? Because we can use the degree of the terms to determine whether the function is odd or even. So that's a third way we could do this. Everybody okay with that idea? Okay. Let's look at one more example here. So let's look at the degrees here first. We'll do that the first time here. So the degree on this one is 2. The degree on the next term is 1. And the degree on the last term is 0. Notice that we don't have all evens or all odds, right? So it's likely that this is going to be neither. You agree? Because they're not all the same. I forget what that name is for odd or even when they're all the same. Anyways, that's beside the point. Let's look at a picture in our calculator to see if it supports our notion that it's probably not either. So again, I'll just type in my function into my calculator. We'll show you. Yep, we're going to do it. So if we do zoom standard, we got a pretty crummy picture here. So I'm just going to make this a little bit taller. So I'm going to change my Y max from 10 to 20. If I look at that, that looks like neither of them, right? It's not, you can see one half has more of the parabola than the other, so it's not even, and it's definitely not odd because it doesn't even go through the origin. So, everybody happy with that? Okay, so it looks like neither here. If we try to do this algebraically, what are we going to need to show for neither? We have to show that f of negative x is not equal to f of x, and f of negative x is not equal to negative f of x. So we just have to check two things to be able to do this algebraically. So either way, we're starting with h of negative x. So, just like we did before, we'll just plug negative x in for all the x's in my h of x. And then I'll simplify. So negative x squared, negative times negative is positive. Negative 3 times negative x, again, is positive. And then positive 9, I don't have to do anything to. If I compare this to my original h of x, is it the same thing? No. What's different? Yeah, the sign on my 3x is different, right? So I know that this is not the same thing as h of x. So we've done this part already. Everybody happy so far? We see how we did that? We just plugged in the negative x and observed that it wasn't what we started with. Okay. So if I want negative h of x, that would be this. And when I distribute that negative sign, I'd have negative 4x squared plus 3x minus 9. Right? If I compare this to this, are those the same? No, right? So I also know that this is not equal to negative h of x. And I'm done. Or I guess I could write here that this is not equal to h of negative x. Oh boy. That wasn't supposed to do that. Everybody okay with that idea? On our odds and evens here? Questions about these? Okay, so I gave you guys like 3 different ways you could determine if something is odd or even. You can look at the graph and visually check. You can look at the degrees of the terms and check. Or you could do this algebraic proof, for lack of a better word, and check. Right? So 3 possible ways to have done that. The next section is about asymptotes. So I need you to think back to your Algebra 3-4 class last year. We talked about asymptotes a lot, in particular when we talked about what topic. If you remember what topic we talked about, we were very concerned with asymptotes. And we spent a lot of time finding asymptotes. Remember that topic from last year. Starts with an R. The other R. What? Not radians. I don't think we didn't talk about those at all last year, I don't think. So, not radical, but rational. So, we talked about rational functions last year. And when we talked about rational functions, we were very concerned, especially when we tried to graph these things, about the locations of the asymptotes. So, when we studied rational functions last year, we saw that there were 3 kinds of asymptotes possible. Do we remember any of those 3 types of asymptotes? Vertical is one, yes. Horizontal is another. And the third kind was the one that everybody hated trying to find, was those slant or oblique asymptotes we had a hard time with. The good news is we're not worried about any of those right now. So we're not going to worry about that. When we talked about asymptotes last year, does anybody remember roughly the definition? I should say an asymptote is a line, the graph, approaches, but does not cross. So let's take a, for example here. This function, and we'll start by just looking at its graph. So the easiest way to type this function into our calculator is to use the fraction options. We can access the fractions menu through a shortcut if we press the alpha and y equals button. That opens up the fraction menu, and the command that we want is just the first one, numerator over denominator. So if I do that, it allows me to type this in exactly how it looks like on my sheet of paper. And I don't have to monkey around with a bunch of parentheses. This is by far the easiest way to type this into our calculator, and much less likely to make a mistake doing it this way. And when I say mistake, I mean like you typed in your calculator wrong kind of mistake. Because you just have to write it exactly how it looks on the sheet of paper. Okay? So I access that fraction option by pressing alpha and y equals. Okay, let's look at the picture. Zoom standard. How slick is that? You guys are just not impressed by that at all, huh? Okay. So, if I look at this, do we see any vertical asymptotes? I see one right there. So you guys agree with that? Do you see any other vertical asymptotes? Good. Where do you see it at? Yeah, about here at 1, right? Oops. Everybody agree with that? So it looks like I have 2 vertical asymptotes. You observe the same thing? If I look, this one looks like it's at x equals 1, and that one's at x equals -3. You guys agree with that? Good. I do also. Do we see any horizontal asymptotes? It kind of looks like there might be one right there, right? Now, obviously, like I had a hard time fitting that in. Notice here, though, the graph definitely has to cross it. Everybody see that? So last year, in Algebra 3-4, we were careful about calling these asymptotes or end behaviors, where we called it an end behavior if we had that crossing happening in the middle, and we just called it an asymptote if there's no crossing at all. Here we're not going to worry quite so much about that, so I'm going to put a little asterisk next to the horizontal asymptote, because we're going to include things like this as horizontal asymptotes for right now as well. Things where you might have a little bit of crossing in the middle, but at the ends you have that same like approaches but doesn't cross behavior. When I say ends of the graph, I'm talking about like the ends of the graph. Is everybody okay with that idea? All right, here's the $64,000 question. So the question is, how do I find these asymptotes? What do I have to do here? Let's start with the vertical. So remember we had y equals x squared plus 3x plus, minus 3 over x squared plus 2x minus 3 was the example problem we've been looking at here. Do you remember how we found the vertical asymptotes for something like this? Just take a guess. It helps to have you think about it. Think back and about that prior learning. Search your memory in between all the episodes of SpongeBob and Riverdale or whatever you kids are watching these days, and see if you can come up with that day in class where we talked about this. Really, probably a month in class where we talked about this, because this was a long unit. It's not the last number on the bottom, although it does have to do with the bottom. It has to do with the entire bottom. To do this, we have to set the denominator equal to 0 and solve. But really, that's not precisely correct. I want to add one more word in here. I want to add in the word reduced. We need to make sure that we've done any reducing possible, and then set the denominator equal to 0 and solve. Okay? So, if I want to reduce a rational function, what is the first thing I need to do before I can determine if it can be reduced or not? Starts with an F. Factor. Excellent. So my first order of business is going to be to factor the numerator and denominator if possible. So let's do that for this example problem. Let's start with the numerator. How do we factor x squared plus 3x minus 3? Or just in general, tell me, how do we factor something like this? What's the procedure? What question do we need to have answered? This is a core skill from Algebra 3-4 that I expect that you remember how to do. It's kind of a bad sign that nobody's spitting out an answer, at least telling me what to do. Okay. We don't need a T-chart necessarily. You want to find two numbers that multiply to give you -3 and to give you +3. And now you might make a T-chart to list those numbers, but I wasn't entirely sure what you meant by, that's what you meant. Okay, so that's fine. Okay, so looking at the numerator, what are the two numbers that multiply to give me -3 and add to give me +3? Well, let's do the multiply side first. What are the two numbers that multiply to give me negative 3? Negative 1 and positive 3, or, okay. When I add those two numbers together, what do I get? Oof, that's a rough start. You get 2. Negative 1 plus 3 is 2. And then you get negative 2. 1 plus negative 3 is negative 2. Do either of those work in this situation? No. So what do we say about the numerator? It's not factorable. So we don't have to do anything there. Okay? Let's worry about the denominator now. So again, we're looking for two numbers that multiply to give me negative 3 and add to give me positive 2. So we want those two. Everybody agree? So what I can do is I can replace the denominator with x minus 1 times x plus 3. Keep in mind, I could do this shortcut specifically because the leading coefficient was 1. If the leading coefficient was not 1, this becomes a much lengthier process. But when we dealt with these rational functions, almost exclusively we were dealing with situations where it was this, or it was maybe if the leading coefficient wasn't 1, there was an obvious shortcut that you could use to not have to do the long factoring. Okay, so here's our reduced, factored, rational function. What I'll do then is I'll take the denominator and set it equal to 0. If I have two things that are multiplied together and they equal 0, I know that at least one of them has to equal 0, right? That was called the zero product property. We used the heck out of that last year in Algebra 3-4 when we dealt with solving quadratics or solving polynomials or any other of these solving problems that eventually turned into a solving a quadratic problem. So if I add 1 to both sides, I get positive 1. If I subtract 3 from both sides, I get negative 3. If I go back to my picture, I notice that matches exactly what we observed above, right? We'll stop here for today, and we'll pick up with this topic.